Okay, distance between two skew lines. Now, they could have asked us what's the distance between these two lines, and one of the first things we would have tried to do is figure out if these are parallel lines, because then we would have known the distance would be the same along any of the points, so it wouldn't really matter what point we found. But if we look at our direction vectors, we do not have parallel lines. Now, technically, we should prove that these are skew lines, and in order to prove that they're skew lines, we'll have to go through the process, put it into Cartesian form or parametric form, and then solve for our parameters S and T, plug them in, find out that they're not the same. We've done this before. We're going to just go on the assumption that we've done this, and we know they're now both skew lines. So the idea from here is we have to find the shortest distance between these two skew lines. Okay? And what we're going to do is we're actually going to turn these lines into planes. Because they're skew lines, let's bring up 3-space. We're going to do a little 3-space experiment here. So let's say we have our 3-space. There's our X, our Y, and Z. And we have a line. We'll say the red one. And he's going something like this. Okay. Through space. And we have a blue line that's probably doing something like this through space. Okay. So I want you guys to kind of get the perception that one is far above the other. They're not parallel lines, but they're never going to cross each other either. Okay. So these are two skew lines in three-dimensional space. Well, what we're going to do is we're going to turn these lines into planes. We're going to figure out what plane, and we'll call the top one we'll call the top one line 1, and the bottom one line 2 here. We're going to figure out what plane this line essentially lands on, or lies on. So, to get this idea, we need two vectors to find a plane, right? We know that this vector here, or line 1, will never touch this vector here. So, we're going to talk about the direction vectors. Our line 1 had a direction vector, or an equation. Let's put the whole thing out here. -2, 1, and 0, plus S, 1, -1, that's 1. Okay? And the other equation for our other vector was R0 is equal to 0, 1, 0, plus T, 1, 1, 2. Okay? These direction vectors are very important because they're going to help us create parallel planes to each other. Okay? Since we know that these vectors won't touch each other, we know that the direction vectors going through the same points. So if we drew direction vectors like that, can I do a red one too? Won't touch each other. Okay? So what we're going to do is we're going to create another vector going through the same point here, but it's going to have the other line's direction vector. Okay? So when we go to create this vector, we'll change the color blue a little. This direction vector is going to have the equation, or going to be going through this point here. It's going to have this direction to it. It's going to have a direction of 1, 1, 2. Can you guys read that? Barely? Let's get a better color here. Oh, I'm in the wrong pen. That's why. 1, 1, 2. Okay? This now gives us two vectors which we can create a plane across. And I'll do my best to try to make a blue-looking plane here. Think of it like these are now on a plane. And we're going to use these vectors to figure out what this plane is. Okay? So we have our new direction vector of 1, 1, 2 going across here. And we're going to do the same thing at the bottom. Okay, we'll change it to an orange color. This direction, or this vector, is going to have the same direction as the one above. The only difference is it's going to have this direction. 1, -1, and 1. And it's now going to create a plane that we'll call parallel to the other one. Because we knew those lines will never touch, when we create planes with them going through them, these planes should be parallel planes. Now the directions don't have to be the same as skew lines, but the planes they're on will have to be parallel if they're to never touch each other. Okay? And if you kind of looked at the original picture we drew, that should have been the idea you were getting from it. It should have been that this red line, the original one, and this blue one, they're not going the same direction, but they're probably the same distance from each other all through space. Okay? So, we're now created planes that are parallel to each other. Well, since our planes are now parallel to each other, we want to find what a normal will be, or we want to find a Cartesian form of the plane. We want to find, in order to find distance, we need a Cartesian form of the plane, so we're going to look at the normals for these two if they're parallel. So in order to figure out the normals of our two planes, we're going to find our cross product of our points. Okay? So let's bring these into numbers now. I'll zoom out a little. So, our direction vectors here. Our point B, which they called 1, -1, 1, and 1, 1, 2. So, if you take a look at this, we're trying to find our equations of our plane. If you want, we could even write our plane up here now. Our plane is denoted by these two direction vectors. So our plane, we'll call this plane 1, is going through the point. Actually, we'll get rid of the R. It goes through the original point, which is at -2, 1, and 0, but it's denoted by two vectors. Remember, our planes are denoted by two vectors, so some scalar of our first direction vector and some scalar of our second direction vector, which is 1, 1, and 2. And our other plane, same idea, just going through a different point. In this case, it goes through this point here, but it has the same direction vectors as the other one. This way we know they're going to be parallel to each other. And T, 1, 1, 2. Okay? So this idea makes sense. We have two planes going through different points, so they're parallel to each other. And the same direction vectors will make each of these up. So now that we have that, we know these two direction vectors. The perpendicular line between them will essentially be the distance line we're trying to go across. Okay? So this perpendicular line is what we need to find. We need to find the normal of these two planes. In order to find the normal of the two planes, we're going to take their direction vectors, and we're going to find the cross product of the two of them. So let's call this direction vector M, and maybe direction vector N. Okay? So M cross N. And this is where we go into our cross formula, which is our A2. So we'll call it MA and NB, just for simplicity's sake here. A2 times A3 gives us -2 minus A3 times B2, which is 1. Then we have A3 times B1, which is 1. Subtract A1 times B3, which is 2. And then we have A1 times B2, which is 1. Subtract A2 times B1, which is -1. So our new normal to the two planes is -3, -1, and 2. Okay. And if you did it the other way and find it the other cross, you would have had a different scalar. It would have looked like this: 3, 1, -2. And if you notice, they're just scalars of each other, these two questions. Whether you did M cross N or N cross M, you would have just had a scalar of the other one. One being multiplied by -1 or the other. So we'll go with what we have. The book went about it this way. We'll go with what we have here. We know our Cartesian form of the plane, or of the normal, sorry, is -3x minus y plus 2z, but we don't know what our d value is, and it's equal to 0. We'll just take the point from the plane we were on. Okay? We could choose any of the planes. Either of them work fine. Well, if we choose a point from the top one, just realize we'll be going to the bottom one there. Okay? So we're going to take the very first point they've given us, negative 2, 1, and 0. We'll use that as our values to plug in for x, y, and z. So negative 2, 1, and 0 to solve for d. So negative 3 times negative 2 minus 1 plus 2 times 0 plus d equals 0. This gives us 6 minus 1 plus d. D is the equivalent of negative 5 in this case. Okay, so we found the Cartesian form of the top plane. We'll zoom in here. So it is written as 3x minus y plus 2z minus 5 is equal to 0. Okay? What we now have to do is, because we're finding the distance between a point and a plane, we have to find, or we have to compare the other point. So we scroll back up. The other point is 0, 1, 0. Okay? So that is going to be our point that is x naught, y naught, z naught. 0, 1, 0. Okay? We're going to be using that to plug into our distance formula. Our distance formula is a, which is negative 3, times x naught, which is 0, plus b, which is negative 1, times 1, plus c, which is 2, times 0, minus 5. And we're doing the absolute value of that. All over a squared plus b squared plus c squared, which is negative 3 squared, plus negative 1 squared, plus 2 squared. This gives us negative 1 minus 5, which is negative 6, all over 9, 10, 14. So we have the absolute value of 6 over root 14, which gives us a value of 1.6. Now, I do want to draw your attention. If you look in the book, they found the Cartesian form of the other plane and inserted the other point. That's the word I was looking for. Put the other point in, but they found the exact same distance. So it didn't matter which Cartesian form of a plane we found, just make sure you use the opposite point to it.